Good morning or good evening, everyone, depending on where you're at. And it's a nice sunny day here in Utah, and cold with a lot of snow on the mountains still. You and I are here in American Fork, Utah. You can see a picture of our site, mountains in the background, and happy to be here and who took the time to join us. Mike Quinn. I'm the Director of Temperature Metrology for Fluke, and I've worked at Fluke and Scientific for about 19 years in working in a primary laboratory here in American Fork as a metrologist and Director of Temperature Metrology. Today we're talking about thermocouples, and some of the things that we're talking about are listed here. Thermocouple characteristics, the theory of operation of how thermocouples work, different thermocouple types and what are they made of, calculations, things like converting voltage specifications to temperature specifications, analyze thermocouple read accuracies, typical calibration scenarios, and then talk about some different calibration schemes and different types of calibration equipment. So, first of all, the thermocouple sensor is probably a temperature sensor in industry, and they are used always. And the reason why is because they're very simple to build, can do measuring temperature. So at a basic level, they are a temperature sensor based on a voltage. It is occurred by connecting two different metals together. And electrical characteristics of connecting these two metals together change with temperature. So as temperature goes up, the voltage will go up. And they're able to make. They are very rugged because the sensor is basically just wire. And what I usually say is that if you unback and take them for what they are very good temperature measurement sensors. But start drilling in on sources of uncertainty or sources of error, and if you really start trying to push them for more and more accuracy, that's where they start becoming really complicated. So we'll be talking about some of these reasons why that happens in our today. So just some basic accuracies. So there are general categories of thermocouples. Basal, so couples like type E or type K. They're made out of metals that are non-null metal, so things like nickel or copper or iron, and they have a little harder time holding the consistency over time. So their public accuracies are typically 1 to 10 degrees range. When you consider that some thermocouples go up well over 1,000 degrees Celsius, that's where you're seeing 10-degree accuracies. Metal thermocouples like type and type R have accuracies, and they are able enough that they can also be calibrated to help improve accuracy a little bit. The accuracies we have here are the off-the-shelf accuracies, like the ASM, special limits of error accuracy, for example. And then thermocouples, just a couple of them are gold versus platinum and platinum versus palladium. Can be accurate, very, very accurate. Comparable with a PRT or maybe even a high temperature SPRT in the 0.3 degrees C to 0.05 degrees C up to 1,000. The problem with gold versus platinum is the gold melts just over 1,000 degrees. So to be careful, you can't. If you come up over 1,000, you'll start approach the gold melt point, and that will ruin your thermocouple. So the of error, again, is, well, the items that we list here, and items, some of them change a lot over time depending on how the thermocouple is used. So inconsistent alloy distribution, this has to do with when the thermocouple is made. How well does the manufacturer mix the alloys together and keep them consistent throughout the length of wire? Oxidation over time, especially at certain temperatures. This is where a section of wire is heated to a point where the metal vaporizes, and the metal vapor moves and then recollects at a cooler spot in the thermocouple. So you start building up a quantity of a certain metal because metal migration. And strain in the wire. Usually, in cases, this isn't even noticeable, but it can cause a change in temperature reading. So if you have wire that's been, say, strained, bent sharply, for example, it could cause the wire to made a little bit, or in some cases quite a bit. Material out there on thermocouples can be fairly hard to digest because it's very, very, I don't know how to describe it, physics. A lot of physics involved in describing how thermocouples work. We have a website by the National Meteorological Institute in New Zealand, MS, and they have a nice little kind of a general to thermocouples. That's a very nice read and has some good basic information. It's easy to understand. The things that they talk about there that we pulled up and brought this presentation, they've done some experimentation where if you bend sharply and in the wire is in a gradient, then you can see as much as a 3-degree shift when the temperature gradient is or when the bend in the wire passes through the gradient region. And the way to experiment with this, if they have a demonstration that they do where they will take a wire that's been sharply with a pair of pliers or something, and then they will take something like a solder iron, will connect it to a readout. They will solder iron along the wire, and where the wire is normal, not or damaged, as the iron passes along the wire, nothing is on the display of the readout measuring the thermocouple. But when the solder iron approaches the bent section of wire, be a 3-degree spike or 3-degree shift in the display in the wire. Type wire, they spent a lot of time studying type K wire and observed as much as 100-degree change in output over 1,000 hours of exposure at 1,000 degrees C. And there are some techniques out there where K wire by putting it in a non-oxidizing environment, flooding the wire with like argon or something to protect it so it won't drift or change a bit much. And they also describe full tests for checking wire consistency or inhomogeneity. They lay a thermocouple on a bench and have it connected to a readout, and to the iron example in testing the bent area or the strain of a wire. They gun and they blow gun over different sections of the wire and watch for changes on the readout. And if they're homogeneous, you won't see the change. So the readout will be around room temperature, around 3 or 25 degrees Celsius or degrees Fahrenheit. And on an area that's inhomogeneous, you will see in the thermocouple. So it's a fairly simple test for testing wire that you think might have some homogeneity issues. Just give you an exact number for inhomogeneity, and that's one of the biggest complications with thermocouple inhomogeneity. Is really possible to determine exactly the overall impact of inhomogeneity will do to your measurement, because it is depending on what the temperature gradient is, and we'll talk about that a little bit more about why is temperature gradient, why does it keep coming up when we're talking about wire inhomogeneity. But so the thumb is, if you see wire that is inhomogeneous, it's recommended to just stop using it, just wire. And we're getting some crazy measurements from wire, then it's a good idea to do an inhomogeneity, see if the wire is or something, so you can move it from a simple little video of this idea of running a heat gun over the wire, and this is right in this, and the controls for it are not coming up. I have to see if we can do that at the end, maybe hover around. Usually it's so many software packages nowadays, you have to hover to find where the buttons pop up, and this one. Okay. All right. Well, sorry about that. It's pretty silly, almost kind of silly, but it basically just shows this moving along the wire, and then when the heat of the heat gun approaches this transition from blue wire to the inhomogeneous wire, then the voltmeter that's connected to the wire will change. And so about that, we'll add a little bit. Okay, the common letter types out there are listed here. Type K probably being the most common that I see, but to all of these in conversations and what the composition of the wire legs of these thermocouples are made out of, and what do you like to look at? And type R, these platinum and rhodium thermocouples. That was an interesting thing for me to learn, was that, if I remember correctly, so platinum is one of the most expensive metals, more expensive than gold. I to joke that if you really say you love someone, you would get a ring made out of platinum. But then later I learned that rhodium is even more expensive than platinum, and so I started changing that to making sure if you love someone, you should have jewelry out of rhodium. But the problem, rhodium is not very attractive, but it is very expensive. So the voltage output is interesting to look at. The reason why type K is so popular is look at the amount of signal that it's able to produce over its temperature range. It will go all the way up to 55 millivolts. So you still have to have a really good voltmeter to measure these small changes in voltage, but you compare that with the type S and type R, where at the temperature you are only getting about 11 millivolts, and that change from only 2 millivolts at the lower temperatures. I think maybe it's to say -2 millivolts to 11 millivolts, but anyway, you have to have a really good voltmeter and these temperature or voltage changes on a type S or type R thermocouple. And it's probably important to go over the theory of operation. There's a lot of misunderstanding of how thermocouples work. Generally, the thought is that the measurement signal is generated out here at the tip, identified as T1, in this circuit. But though, in general, you can consider that the temperature that we see on the display of the readout is the difference between T1 and T2. However, even not totally correct, but that's generally what's going on, and it works fairly well. That's something else we need to talk about here before we move to the next slide. Well, actually, let's talk about some more things here. So the thermocouple wire, one identified as A, and the other is identified as B. And T2, you notice that these two wires transition from the thermocouple wire to a blue wire that's labeled as C. That's representing copper. So in almost every thermocouple measurement scenario, eventually the thermocouple wire will be another metal, and as possible, we try to control that so that it's always touching copper. And so we'll talk about that a little bit more here in a moment. T1 is often referred to as the major junction or the hot junction, because at the end of the thermocouple that goes into the heat or the area that you are measuring. And T2 is referred to as the reference junction or the cold junction, because it's usually kept close to room temperature or maybe in a zero bath. So let's just go with that a little bit more here. I think they said thermocouples work by the voltage potential varying as temperature change. The voltage varies from -15 when you're 0 Celsius to about 20 volts at the high temperatures, depending on thermocouple type. The output is proportional to temperature, but it's not linear. It's fairly linear, but definitely not perfectly linear. And this is a key item here in describing how thermocouples work. Voltage potential that you see is by differing electron densities that are along temperature gradients. This is why we talk about things can start happening, like if the wire bent and exposed a gradient region, we can get readings. So, the way couple works then is if you even think just a single piece of wire, if you lay a piece of wire on a table and use a torch or heat or solder iron to heat up a section of the wire, see it, but inside the wire where you have a hot area of the wire versus cold area of the wire, electrons are being pushed around, and it was because of the temperature gradients and the clumping or the gathering of electrons, more electrons in some areas than others. This causes voltage potential differences, and it only happens over gradient regions, and it's called the Seebeck effect. Now, if the wire isn't very useful because you can't do it, as soon as you touch needs to it to measure the voltage potential on it, you're creating basically creating a thermocouple circuit, and we'll get into that a little bit more. But that idea of heating a section of wire and creating a difference in density of electrons is the basic operating principle of a thermocouple. And thermocouple wire is never perfectly consistent, so the other thing to consider is that the entire length of the thermocouple is the sensor. So all of the thermocouple wire is involved in producing a voltage for you to measure. The majority voltage is generated generated in the gradient region. Technically, there are tiny little gradient regions throughout the entire length of the thermocouple. Like if the thermocouple passes through a typical room, it's around 23 degrees, but if you zoom into micro levels, you will see that there are this is always a hard word to say, infinitesimally small temperature gradients throughout the length of the wire. Now, true that as the wire passes through a room, the temperature gradients are fairly small, but they're there. They are there, and they are contributors to the overall circuit. Okay, so when you have these two different pieces of wire, the thing needed to make a thermocouple is to have two different pieces of wire that have different thermal characteristics. That way, you are able to generate a voltage between the two of them touching. And join these two pieces of wire together, you create the junction, which is, again, T1 in this diagram. And then you have to connect something to the wires to be able to measure them. So eventually you either have to connect copper wires that you can then take to your voltmeter, or you connect the thermal wire directly to the meter, but the wires touching connectors in the meter. What method you're using, whether it's copper wire or the wire is touching a copper connector in the meter, need to know the temperature of T2. So we need to control T2 and identify what it is. And we do by either in an ice bath or some temperature. It can be even just a liquid bath, the temperature of it, because you have another temperature sensor telling you the temperature. Or if connecting to the meter, we'll tell you here a little bit more about what happens then when water is connected to copper connectors in a meter. Okay, so coming back to this diagram, though, the junction 1, not where the voltage is produced by the wire. T1 is just in the two dissimilar materials. Seebeck effect combines to create a voltage. The voltage potential is being generated wherever the temperature gradient is at on wire A and wire B. So if you have for example, and you put the thermocouple in a furnace, if the furnace is uniform temperature-wise in the bottom of the furnace where the measuring junction 1 is, there isn't much voltage generated by the wire in that region. Where the voltage generated is at the top of the furnace, where it transitions from room temperature to the temperature of the furnace. The reason why this is important to think about, because this is also where there's a good chance that the wire is changing composition because maybe the temperature where the wire transitions into the furnace is an oxidizing temperature. And as the wire or mace furnace, you're creating a zone of wire. What happen is that's the coldest region of the wire is where it leaves the furnace and in room temperature environment. If you have set at high enough temperatures that the wire is vaporizing, or certain components of the wire are vaporizing, they will move along the wire until they reach a point where the wire is cool enough that they can recollect. So it's interesting that the region in the furnace where you are generating voltage is also the region where there's potential for things to start happening to the wire. So anyway, some interesting the thermocouples in that sense. Okay, so just one more quick thing about these two junctions, just to really nail it down. Junction is the thermocouple circuit where transition from thermocouple wire to copper is made. and is usually maintained at 0 degrees C or close to room temperature. Main junction is the thermocouple circuit where the two thermocouple wires or legs are connected. Basically just completes the circuit, allows us to see a voltage potential junction that goes into the area being measured. And we have a picture of a typical reference level thermocouple, and those where the junctions are at. Already about how reference junctions are controlled. So keeping the reference junction at 0 degrees C is the easiest method because the tables that you look at on the website or in the ASTM books or in any of the thermal manufacturer's websites, that is in the temperature versus voltage tables, our reference junction being at 0 degrees C. So use an ice bath and you keep the junction at 0 degrees C, then you should see a voltage output that matches very closely with tables. You can then test the wire and make sure that it complies with the allowed range of voltages that are applicable for that thermocouple. If you keep the reference at another temperature, like room temperature, you have to compensate for that. You have to know what temperature is and then convert that to a offset and cancel that from your reading. So sometimes you'll have a meter that is able to do that automatically for you, and it has an internal junction compensation circuit. I'll show you or a circuit to demonstrate what that looks like. A typical ice bath like we use in our lab, our laboratory, the picture isn't really ideal, but basically it's just a tall, narrow vacuum flask, and we just up with shaved ice and with water. And now there is some technique to making these. It's not like a consistency. It's more like a kind of snow cone with just enough water to fill in the gaps between the wire or the ice. But they very well, and so you can get really good measurements from an ice bath. Here's an electrical diagram showing how the wire in yellow and red is the copper wire down inside this bath. This junction connects the thermocouple wire to the copper wire. Doesn't be anything special. We, like in laboratory, for example, we just the tip wires together and then apply a solder to hold them together, and that's for calibrating. And we don't really worry about the fact that we're bringing in solder in this connection because this in an isothermal zone. The temperature is 0 degrees throughout this bath, so there's no chance of voltage being generated by these different materials mixing together. And here's an example of a circuit where thermocouple wire is connected directly to a meter, and the meter has copper connectors inside of it. But that's where the junction is at. We have to measure temperature as best as we can. So there's a temperature sensor here right next to the connector, and it tells us what the temperature is. The meter temperature into consideration and basically compensates for it automatically to give you the correct reading on the display. This is a picture of one of the Fluke products. It's a high capacity module. So the temperature sensor is right here in the center, but thermocouples connect on several different terminal blocks that this card, and the specs on this thermocouple compensation circuit, reference junction compensation circuit, are fairly large because there's so much space separating the where the thermocouples connect versus the temperature sensor. But the goal with this one is to have high capacity to be able to connect lots of thermocouples to it. Compare that reference compensation circuit, the specs for it, with one that's designed for reference level work. So showing you is from the 1586A DAC, and it might be hard to see, but this high capacity module, the CJC accuracy, is listed here, and it has a 0.6 degrees C specification. So large. The 2065 shown below, this is reference grade thermocouple readout, and so its internal CJC is 0.05 degrees C. And the difference between these two is mainly that with the 565, the temperature sensor is right between the connectors where the thermocouple wire connects. So the connection is very, very close, and there's other things too that help make up a much lower specification. Now we need to talk a little bit about if you have a voltmeter, what the temperature accuracy of the voltmeter when measuring a thermocouple. And the way to calculate this is you get the uncertainty of the voltmeter. So that's what goes on top on this equation is the uncertainty of its voltage, and you do that by the sensitivity of the thermocouple at the temperature of the measuring junction. For example, well, I actually have a sample to calculate here, but before I get ahead of myself, this S sub MJ value, if you don't know what it is for your thermocouple, well, first let me say you need to know what it is at the temperature that you are measuring, because it does vary depending on the temperature. So the easiest way to find out what it is you just look at a typical thermocouple like the one found in the ASTM book or on the NIST website, and all you have to calculate the change in voltage over a 1 degree Celsius change. And usually tables are already set up in increments, so it makes it really easy. You just look at the two adjoining voltage values at the temperature that you are working with and calculate the change in voltage, and then that way a voltage over change in temperature or over a 1 degree Celsius change in temperature. Okay, here's an example. Test thermocouple that's being measured at 1000 degrees C. And the meter that we're using has a specified voltage accuracy of 0.02 millivolts. So to divide that by the sensitivity of the Type S thermocouple, so we look at the best couple, and with the sensitivity at 1000 degrees C is 0.0115 millivolts. So 12 microvolts per degree. So that's why you have to have a pretty meter to be able to measure these successfully. And a meter that's able to measure with low voltage noise is able to get a stable reading. It's math, and that is a 0.17 degrees C equivalent. So 2 microvolt thermocouple at 1000 degrees C gives you a 0.17 degrees C temperature. So no thermocouples like Type S can be challenging to measure. Now, part of the readout accuracy or a base accuracy component or uncertainty component for is the reference junction accuracy. Now, you can really RSS or combine the reference junction accuracy with the voltage accuracy that we just now calculated, but there's a technique that testing if you consider it, and it will work out for fit. Where if you consider how a thermocouple measurement circuit works, you have two different junctions. You have the junction represented here by sub MJ, so the sensitivity at the temperature of the measurement junction, and then you have the reference junction. And so consider the ratio of the reference junction sensitivity to the major junction sensitivity, this will create a reducing effect for the uncertainty of our reference junctions. So let's look at this works with some numbers. We have the same measure we're making, test thermocouple at 1000 degrees C. This would be at 1000 degrees C is on the bottom. It's 0.0115 millivolts per degree C. At the temperature of the reference junction the reference is at 25 degrees C. The sensitivity is 0.006 millivolts per degree C. So we multiply our reference junction certainty 0.05 times this ratio of the two sensitivities. We end up with certainty 0.026 degrees C. And we don't aim to go into that in detail in this presentation, but basically, if you think about it, it's because of when measuring in a thermocouple circuit, you have both of these junctions contributing to the overall voltage. So consider how sensitivities combine with each other, and it's a really interesting thing to think about. So I was just showing now we have voltage accuracy that's combined with the reference junction accuracy, and just do that by RSS. They are two independent variables. Okay, now I'm going to pick up the pace because that was the most complicated part of our today is how thermocouples work and some of these calculations. Now let's talk about some calibration schemes. Generally, most people are tolerance testing thermocouples, especially the base metal. This is where you are picking some measurement points and you're checking the thermocouple against the specified accuracy of the thermocouple. And you either reject it or accept it based on if it's in tolerance or out of tolerance. Then the method some use, especially with noble metal thermocouples, we do a lot of characterizations of noble metal thermocouples. This is where you gather enough temperature versus voltage data that you can either calculate a new thermocouple curve or new thermocouple coefficients, or you may just calculate offsets or report your customer, so the customer can then apply offsets to compensate for the errors that you see during calibration. So to consider, really important is, especially with base metal thermocouples, but it also applies to noble metal, I suppose, is that because the voltage is generated over gradient region, if the calibration setup has a different gradient region than where thermocouple is used, if thermocouple wire is inhomogeneous, you get different results in the application versus when it's calibrated. So it gets controversial. Some they have opinions that thermocouples can't be calibrated because of this. And so what's important, if you do calibrate thermocouples, one, you subscribe to them calibration report where the gradient region is located in the instrumentation that you used for calibrating the thermocouple, and decide if consider application. If it's basically summarize that, think that if the region in the calibration process is 20 centimeters from the tip of the thermocouple, but when the thermocouple putting it inside of a furnace where 30 centimeters away from the tip of the thermocouple is where the gradient is at, you're using a different section of the wire than you're calibrating in the lab. That's why it gets all crazy when you start trying to drill on sources of uncertainty with thermocouples. Yeah, with base metal thermocouples, just to calibrate them may cause them to change, especially at higher temperatures. So the rule of thumb is if you're using above 300 degrees C, they're not, you may be able to calibrate them. It's kind of goofy that think that the calibrating it will just cause it to change, and you may not be able to capture what your customer was seeing. But 300 though, they are very reducible and definitely value in calibrating them. A lot of calibrations are done on site or in situ, and these are done by a combination of, sometimes typically there is a comparison calibration where the thermocouple is brought out and put into a heat source, or like the right-hand picture here, and compared with a reference temperature probe. But oftentimes in a transit situation, the thermocouple is simulated. So you connect a thermocouple simulator to the transmitter, and you verify that the transmitter is measuring thermocouple voltage correctly. The assumption is that the thermocouple is working just fine. But we just got done talking about all the things that could cause thermocouples to change a lot. So if you can also verify the thermocouple measurement areas, and but it can get very tricky in on-site calibrations. Now in our lab, it's a lot easier. You have a lot more options. And in our laboratory, we calibrate thermocouples by fixed point, but we only calibrate metal rinse grade type R and gold platinum thermocouples. But most thermocouple calibrations are done just like any other temperature probes. You bath that provides a temperature, and thermocouples in the furnace or the bath at a reference probe, and you make a thermocouple and connect it to a readout like shown here in the left-hand picture. See the time on my computer because there's a. Oh, okay, great. So let's see. Comparison calibration scheme is where you connect or you compare unit under test thermocouple against a reference temperature probe, or possibly the display of a calibrated source or heat source. Typical heat sources used for thermocouple calibration are dry wells, furnaces, and baths, and we'll show some more pictures here. The one shown here is a dry well type. Well, meaning there is no liquid used inside in the unit. It's just a metal block with holes drilled into it will accommodate the thermocouple probes. UUT probes are connected either to a reference meter provided by the laboratory, or probably they stay connected to a readout that's provided with them, so that a system calibration can be done. So let's say that the majority of thermocouple calibrations are happening in just like the metrology well, the Fluke metrology well. These are calibrated furnaces, and the display has an assigned accuracy. For applications, there is this small portable high temperature thermocouple furnace that's popular for our thermocouple customers. But because it's so small and has such a large gradient side of it, it's not an ideal instrument to use. But for high temperature applications, it's really about there's a lot of options. So if you have a better uniformity for high temperature applications, then you need to move toward a horizontal furnace, like the one shown in the lower right-hand picture. But then furnaces have depth to them, so they really only accommodate longer thermocouples. So the small little 12 long thermocouples that you see all over the place can only be calibrated in these furnaces. They're long enough to be calibrated inside these big horizontal furnaces. Let's see. The two specifications to consider for the heat source are temperature stability and uniformity. So temperature stability describes how well can the furnace maintain a temperature set point, up and down in temperature as you're trying to measure, or is it nice and stable? And uniformity describes how consistent is the temperature throughout the furnace. Does the furnace have large temperature gradients throughout the working of the furnace, or small temperature gradients throughout the working area of the furnace? Another component in calibrating thermocouples is the readout. And I already talked about the readout somewhat. A lot of people use voltmeters to measure thermocouples. So a precision voltmeter works well, but sometimes a DV digital voltmeter doesn't have a couple mathematical equations inside of it. So you do the to temperature calculations yourself, and that can be kind of a pain. And then, so thermocouple readouts, of course, have the thermocouple math built into them, and there are different techniques for entering either sets for a calibrated thermocouple, or there are calibration coefficients that can be entered for thermocouple, and there really isn't an industry standard for so it can be a little frustrating for use. I have a lot of questions people ask for help converting. I have a couple calibrated at NIST. They gave me the function coefficients. I don't know how to put them in readout. Can you help me out with this? And anyway, it gets all complicated. Unfortunately, there isn't a clean standard like there is for PRTs with the ITS 90 equation coefficients. So let's see. Some combined systems, like in this picture in the lower right-hand corner, furnace is designed to work with this readout, and they connect together so the readout will actually control the furnace and will take readings on the thermocouple. It has the built-in math, automatically convert voltage to temperature for you, has lots of channels. But the advantage is it also measures PRTs. So you have the option of bringing in a reference grade PRT. So we'll talk about that next on reference probes. So, quite commonly, we see people using ref PRTs, platinum resistance thermometers, to provide the reference temperature for thermocouples. They also, for higher temperatures, quite often will use reference grade type S and type R. And usually they do that. They have them calibrated by fixed points so they can get low certainties. One more component for the thermal calibration system is how you handle the reference junction. And we've already talked about how to have the readout handle it for you, but typically the uncertainties are a little bit bigger. Here's an option where if you don't want to be bothered with making ice bath, then you use a basic ice bath simulation furnace like this one, where its job is to just stay at 0 degrees C, and some wells where you can insert the thermocouple reactions. So some tips to consider when you are using equipment like thermocouple furnaces. First of all, keep in mind that the curves over here show a depth where stability arrives before uniformity does in a furnace. So here's an example of two probes that were put inside of a furnace like the one shown here, and were put in slightly different locations. One's they're close to each other, but in slightly different locations. And the control probe in red. Well, let me back up a little bit. We started off at room temperature, and then we ramped the furnace up to 500 degrees Celsius. So the control probe overshot a little bit, but quickly stabilized. So the display of the furnace indicated that everything was nice and stable. which was, but the other probe in blue, it in a different region of the furnace may have been closer to a heater, so temperature spiked and overshot more. Something to consider is the potential for overshoot. In the case, the furnace was ramped at its just ramp rate possible, and so we set ourselves up for an overshoot. It overshot more over 100 degrees and took much longer to eventually equilibrate and stabilize and equilibrate. So it wasn't until about the 1800 mark, a little bit before the 1800 mark, where we finally saw uniformity settle inside the furnace to where the thermocouple readings were much closer. So if we've taken data at the 1648 time where possibly the display of the furnace looked nice and stable, we would have measured some significant error, 5 degrees error. Being another 40 minutes, the furnace became very, very uniform, and the difference between the two probes became much, much tighter. So sufficient time for stability and uniformity to be achieved. We have this picture because it shows two different configurations for calibrating thermocouples. The one on the left is an open cavity method where you bundle the thermocouples together, and typically in this situation, the reference probe is in the center, and then the UUT probes are added to the reference probe in a bundle. The hand picture is where an equilibration block is used, and we'll look at this here in a moment on what spec changes or the differences are. Here, basically a standard set of uncertainties that you would consider for a thermocouple calibration system. You have to consider the readout accuracy, the junction accuracy, whether the readouts reference junction compensation circuit, or if you're making your own ice bath, accuracy, uniformity, so how consistent is the temperature inside the heat source, stability, and this is seen by being 30 or 40 readings, being the standard deviation to see how stable the readings are. And there's some other sources of uncertainty, like homogeneity, potentially. I thought I had. I apologize. I thought I had a slide coming up showing the differences in the specifications between these two instruments. I'll have to get that. But basically, the uniformity due to equilibration block, the uniformity of the equilibration block setup is a little bit better. But then there isn't as much flexibility as using the open cavity. So some costs there. Some people prefer the open cavity because they can put in a larger variety of probes, and they like to bundle probes, but they have to be careful with what the uniformity might be inside the furnace with these different configurations. Equilibration block is not simple, but now have to have probes that are long enough to go all the way into the end of the equilibration block, and in room for there are 4 holes in the equilibration block. But anyway, that for presentation, the last slide here, a link to the NIST Thermocouple database, which is very, very handy. These are the same. This is what the ASTM thermocouple tables are based on, and so NIST has a nice little tool here that helps you the letter type that you were working with and the temperature range that you were working with. We'll have a link to the New Zealand NMI, and there's some interesting documents they have about thermocouples, and we also list some other references that are typical for thermocouple calibration, like ASTM and NIST, SP250, and NIST Monograph 175. So that I'm going to time over. Let me show a picture in here somewhere that would help with that. I probably do need to get a better picture. The region is where temperature of the furnace, or the whether it's a bath or a furnace or an oven, it's basically wherever there is a significant change in temperature. So when we talk generally about a gradient region, and that's where the voltage is produced, the area in the heat source where it transitions from the temperature of the heat source to room temperature. So it'll be over a fairly large area. Like if you horizontal furnace we were showing earlier, the gradient region is maybe centimeters long at the opening of the furnace. So again, that's where it transitions from the temperature inside the furnace to the temperature in the room. It's where the voltage is generated by the thermocouple wire.
Next question is, how often should we check for inhomogeneity?
That's a good question. I've contemplated having a separate webinar just about homogeneity, because it's a topic for laboratories that are calibrating thermocouples. Like, for example, we have to do an inhomogeneity test when we rate type S, type R thermocouples. It's required for any accredited laboratory. But a lot of controversy out there about how to measure inhomogeneity, and then even if you go out and buy the world's best wire scanner, people can't say for sure what the uncertainty is by the inhomogeneity. But make attempts to calculate the uncertainty is. So how often should you measure inhomogeneity? Well, it depends on the level of uncertainty that you are trying to achieve with your thermocouples. If you're trying to go beyond the AEM specs, then you have more obligation to measure inhomogeneity. Definitely, if you're seeing errors with your thermocouple wire, that'd be one of the first things you want to do, is just do a quick inhomogeneity test. If you just need to get rid of the wire. Now, thing that's related to this is a lot of thermocouple manufacturers will do. They will test samples of thermocouple wire on a roll. So they will, as a matter of fact, STM has some guidelines for this, where you make many thermocouples with wire from one end of the roll, and make so many thermocouples with wire from the other end of the roll, and maybe even take wire from the center section of the roll of wire, and it's batch cal. And they will all of these thermocouples show that they all agree within the published specification for the thermocouple. And it is, a homogeneity test. You are testing the wire consistency throughout the roll of wire. So that counts for inhomogeneity. There's risk that there are other sections of the wire that may have other inhomogeneity that you don't know about. But so that's one method is if you're making new thermocouples, well, always multiple thermocouples, get an idea of how consistent the wire is.
Next question is, what is the preferred solder type for thermocouple junctions for best results? Is there recommended minimum silver content or flux type?
Well, there really isn't. It's really simple, because if your reference junction, the question's about the reference junction, right? Because normally you don't solder for the major junction. Okay, yeah. So for the reference junction, when we solder the wire, standard low temperature was 10. A few years ago, we had to stop using lead with lead. So now we're using a little higher temperature solder, and it really isn't any standard. As a matter of fact, I've been at some laboratories where they still use mercury cups because they are convenient. You have a bit of mercury in the bottom of your junction or tube, and use the wires down, both touching the mercury, and that makes the circuit. So you don't have to worry about using silver solder or anything like that. Just standard whatever you'd use for electronics.
The next Mike is, he's mostly familiar with Type T thermocouples and use them for the K validator. And his question is, about the way of preparing the hot junction, what's the best practice? Can you tie wires together separately and then join the ends and weld them, or is there a better way to do that?
Well, the rule of thumb with making a major junction is to make it as small as possible and the least disruptive to the wire as possible, because in the we said that it isn't generated by the major junction, but the idea is that the major junction is in isothermal zone of the furnace, and to make sure that happens is that you make it small as possible. You disrupt the least amount of wire possible. So I don't twisting the wire together and then welding it, because it may drain in the bottom centimeters of the wire. Again, there's probably that's not a huge issue, but best practice dictates that you twist the wire and you put the two wires next to each other and weld them together with the smallest junction possible, just to help ensure that you're not creating inhomogeneity on the wire. Like for example, you wouldn't want to take a torch and heat up the 2 or 3 centimeters at the end of the thermocouple and to make your junction. You want to use fine-tipped torch. A lot of labs use a water torch. They're really handy because you don't have ethylene or hydrogen. You just use water and a chemical that hydrogen. I don't know exactly how it works, but it makes a very, very small little flame, like the tip of a pencil, and you can use that to heat up just the very, very tip of the wire and then weld the wires together. Laboratories use these spot welders that some manufacturers make these things where you just take 2 wires and you push them inside the welder, push a button, and it arcs the wire together in a nice, simple little way. Sometimes they're just not quite clean as somebody doing it with a pencil torch. But anyway, just some different thoughts there on making the major junctions.
Is there a Fluke voltmeter model that you recommend for reading the signal from a thermocouple?
So in the laboratory, we are doing calibration, so we're interested in really, really good voltage. So we use an 8508A. That has worked well. Its standard uncertainties or accuracies are good enough to get some really good voltage measurements on just some type R. But that's it's grade. Trying to get the lowest uncertainties possible. We've also used Keithley nanovoltmeters over the years, but their off-shelf specs aren't good enough. We have to characterize them ourselves to get the accuracy, but they hold the accuracy really well. So 2182 voltmeters. Essentially, like the Fluke 8846A. I have to admit I haven't looked at the specs on that, but probably for base metal thermocouples would be fine. It doesn't have any, I don't think, any voltage temperature thermocouple conversion side of it. Now I'm more familiar with the Fluke Heart products, like the Black Stack instruments in the 5086A. The 50A is kind of nice because it's similar to a DVM in that it measures thermocouple and it measures PRTs and thermistors. So you have a variety of options. But anyway, so recommendations.
Okay. The next is there any possible impact due to the coming redefinition on the S unit?
No, not for thermocouples. Nope. They fortunately they do a clean conversion, and the IX90 math for now will stay the same. Temper fixed points will stay the same. Is the goal. It's just definition. Eventually, they may do new values for fixed points and the math and stuff, but for IX90, but that's still down the road. Good question for sure.
Okay, the question may be a little variation of what we talked about before. Is there any best practice for making the temperature measurement at the UT location and the meter at another location?
Sure, if that question's asking if like there's a certain distance that should be done. You know, it's maybe leading to the idea of levels of thermocouple wire. Not sure if we could get a little more clarification on that, Steve. Or do you have any thoughts on what?
Yeah, maybe we need a bit more information. If you could, then we can get a better response to that. Let's move on to the next question. Correct to assume that using a thermocouple in an application with a small temperature gradient, say measuring 0 degrees C, that the overall errors would be less?
Yes, I think so. Let me think about that for another minute here. Small temperature gradient. For example, the reason why ice baths are used for junctions is because they are so homogeneous temperature-wise, or so uniform. And you still have to be careful with an ice bath if you and you don't keep it replenished with fresh ice. And let's say, for example, at the bottom of, since ice floats, this is the potential that happens is you get liquid water at the bottom of the ice bath that's at a different temperature, and that's possibly the temperature of the ref junction that you have in there. But yes, I think that's a correct statement that for the ice bath, if you have better uniformity, smaller temperature gradients, and then we get better with less. Now, possibly related to this also is if you can make wire in a scenario where the temperature that you're measuring is uniform, and then there's a very sharp transition from that temperature to room temperature, because it provide a method for you could insert the wire at different depths and do a wire inhomogeneity test. if the gradient is spread out over a large area, it becomes a little harder. You can move the wire in and out of the furnace, for example, if that's what we're working with. But if the furnace itself is not uniform, it becomes hard to know where the change in the readout thermocouple, the thermocouple's temperature. You don't know if it's because the furnace is not uniform, or if it's because you have a homogeneous piece of wire. So people who do wire scanning for inhomogeneity testing, they typically a stirred liquid bath, so they get really good uniformity, and then they do some tricky things at the top of the bath where it transits from the temperature of the fluid to room temperature to try that area as small and clean cut as possible, so that as they pass different sections of wire through that region, they can really pinpoint where there might be inhomogeneity in the wire. So yes, in general, having a furnace with good uniformity, sharp gradient region produces better results. So that took a while to kind of come around to.
All right. This Mike was clarifying that earlier one. So he's really wondering is the distance. So if you're making the measurement from the UUT to the meter, is there on that distance?
Oh, okay. So yeah, that's a question, because we see there's some rule of thumb out there that I've seen where I think main is to consider are signal loss. There isn't really any current flowing, very minimal current flowing in a thermocouple. So fortunately, that helps a lot with signal loss. And measure thermocouple for a long distance or long length of thermocouple wire. However, we'll have things that can happen like the couple conduction. You could have in the cabling, you could have enough parasitic resistances and cadences and goofy things going on that it becomes more and more of a challenge to measure them over a long distance. That's one issue, is signal loss. Second issue is how are you extending the thermocouple? So most of the time, if you're using a low cost thermocouple wire, then you can just make the entire length out of the same wire, take it off the roll and make a 100-foot long thermocouple. But at times, the thermocouple wire is fairly expensive, so you're using extension wire from your thermocouple extension over to the meter. So for like in factories, sometimes you will have maybe 50 or 100 meters of from the couple to a control room and wires being used. Well, I don't remember exactly off the top of my head, but there's some I've seen that if the temperature difference between you take the max and min temperature, the where the extension wire is being used, and if it's greater than 2 degrees or 3 degrees, you need to start adding additional or consider additional error caused by gradients over the extension wire. So sample in a factory, if the control room is at 23 degrees, but through the factory temperature approach 30 degrees Celsius, the extension wire is now going to start contributing error out of its specifications or additional error that you would need to consider. So some of the complications with measuring over a long distance. Things like one more thing is wire. People describe to me situations where wire is strung across the shop floor, and if things or like forklifts run over the wire, things like that, then that can also start changing the readings that you get. So anyway, some thoughts.
Okay, Mike, the next question is in your chat window there. If you want to take a look at that one,
We would like to read air duct temperature of a 4-inch diameter tube, can I use 5 thermocouples and connect them in parallel and calibrate this 5 thermocouples? Oh yeah, I see this a lot of in several factors where it's one reason why thermocouples are popular. You can make a lot of them and can do lots of interesting temperature uniformity tests with thermocouples. So this is a very common application where you will take multiple thermocouples and bundle them together into a nice uniform heat source, and you will check them and verify that they all match. And matter of fact, the 1586A has a feature where what it's called, but it's something. It's basically this concept of all the couples are bundled together into a heat source, and then you push a button and it automatically detects the difference between them and normalizes all of them. So it does a quick calibration. I don't remember all the details, like if that applies over multiple temperatures or if that's just at one temperature. Absolutely, that's application applied in any different scenarios for making, just describing temperature gradients inside of an air duct.
All right. The question is tolerance of a thermocouple. I think you may have touched on here.
Yeah, that's something that would be nice to have in that one table we have is, or maybe I passed it. We should add a column here for with the ASTM tolerances for thermocouples. So I'll say is that it varies with each letter type, and the most tolerances are type S and type R. They vary from, as a matter of fact, I have those numbers here. Type R. Basically, the touch tolerances are around 0.6 degrees C. Also, at the higher temperatures, go up to as high as 2.7, and that's special limits of error specification. There are two level specifications for each letter type. Metal tolerances usually they start out at the best they get is 1 degree C, but quickly can go up to as high as 10 degrees C, depending on temperature and the letter type.
All right. Next one, Mike, is what thermocouple works better in the temperature range from 196 to 20 degrees C? What would be the best in that range?
Okay. A lot are using type E or type T. That's type E is oft used over the in type T. Type K. I'm trying to remember the reason. I really hear of people using type K though at really low temperatures. It seems like it's just type E or type T.
Okay. Next question is the limit on the resistance of thermocouples specifically all implantable thermocouples can have resistances of 180 ohms?
Where's Steve?
Right here.
That's a good question. I haven't seen any literature driving the required resistance of the thermocouple insulation. That's a good question. To take that in consideration and see if there are some recommendation out there. Because some of the wires are so small. Now, the underlying principle, I think the reason why it's not mentioned much is because again, the thermocouple circuit. Well, some I've read basically that there is no current in a thermocouple measurement. It's just voltage potential with no current. But in reality, when you get there's current, very, very small current. I have seen an idea of how small the current is, but there is such small or low current. That's why you can measure even a millivolt over a long split thermocouple wire. But it's a good question. I'm going to we'll see if we can come across anything if it's on this has already done research in that. Send it to the chat. Any thought? So sorry, I have an answer. It's a very good question.